Okay. Now, in yesterday's class, we are discussing with ideal Rankine cycle. Okay. Today, I'll discuss one problem related to the actual Rankine cycle. Okay. I hope all of you are seeing the contents on the screen. Okay. Before that, first I'll explain the problem. Okay. Steam enters the turbine of a steam power plant operating on Rankine cycle at 10 bar pressure and 300 degrees Celsius. Okay, so the condition of steam at inlet is 10 bar and 300 degrees Celsius. 300 degrees Celsius means obviously it is superheated temperature. Whatever the condition of steam at the entry is nothing but your superheated steam, because the temperature is 300 degrees Celsius. The condenser pressure is 0.1 bar. Steam leaving the turbine is 90% dry. Calculate the efficiency of the turbine and also the cycle efficiency, neglecting the pump work. Okay, so these are the things you are going to calculate. Okay, so first, before starting, you have to draw the TS diagram. Okay, so 1 to 2, because you have to start, you have to take little bit above the saturation curve. 1 to 2 is your isentropic expansion. 2 to 3 is your constant temperature heat rejection. 3 to 4 is your pump work. 4 to 5 is your regeneration. 5 to 6 is your isothermal heat addition. 6 to 1 is superheat. Okay, at 0.6 we are having the steam at 100 degrees Celsius. Okay, then 6 to 1 is the amount of superheat. Now the given condition is 10 bar pressure, means it is a boiler pressure. Boiler pressure is your P6. Okay, don't take P1. It is the boiler pressure is P6. It is 10 bar, and we are also representing it as PB. And then at T1, the temperature at point 1 is 300 degrees Celsius. That is called superheated temperature. Next, condenser pressure. Condenser pressure is nothing but P2. P2 and PC both are same. It is 0.1 bar, and the dryness fraction of the steam is given 0.9. Okay, whenever they will give the dryness fraction like it is like this, it is the actual steam, means actual Rankine power cycle. Okay, next we have to find out the adiabatic efficiency of the turbine. Okay, as I said, adiabatic efficiency is your actual enthalpy drop divided by ideal enthalpy drop. H1 minus H2 dash divided by H1 minus H2. Okay, so same thing we studied in gas turbines also. H1 minus H2 dash divided by H1 minus H2. Okay, now so you have to refer the steam tables. Okay, so don't take normal this one values. We are having option called a superheated steam. Okay, because the temperature of the steam is above 100 degrees Celsius. Okay, now whatever is there in the third column, actually we are having the steam properties of superheated steam. Don't take the wet steam. Okay, and in the steam tables we're having option called as superheated steam. You have to refer the superheated steam, and corresponding to a pressure of 10 bar and 300 degrees Celsius, you have to find out the values. We are getting the values as H1 is nothing but the enthalpy. of steam to convert 1 kg of water into 1 kg of superheated steam from steam tables corresponding to pressure of 10 bar and 300 degrees Celsius. We are getting the value of H1, that is enthalpy, as 3052, and Sg means it is the entropy. So you'll get in the table only 7.125. Okay. So enthalpy will be more as compared to your wet steam, because the more amount of the heat is supplied to convert 1 kg of water into 1 kg of superheated steam. And at condenser pressure 0.1 bar, we are having, this is V1. V is nothing but your specific volume. This also we are getting from steam tables. You see 2 to 3 is your condensation process corresponding to condenser pressure of 0.2 bar. We are getting the specific volume as um, corresponding to pressure of 0.2 bar. We are getting the specific volume as 0.0010 meter cube per kg, and meantime we are getting the value as HF2. You remember we are having the HF2 values in case of wet steam, because condenser, whatever the condition of steam is in wet condition, that's why you are getting HF2. HF2 is nothing but your sensible heat. Sensible heat is nothing but the amount of the heat required to convert 1 kg of water into 1 kg of wet steam at saturation temperature, that is at 100 degrees Celsius and at given pressure. That is the definition of HF, or sensible heat. So corresponding to pressure of 0.1 bar, we are getting the specific volume and HF2 as 191.8 from the steam tables. And these are also the values we are getting from the steam table only. That's why first, as soon as the values are given in the problem, first you have to analyze all the properties, and you have to write down all the properties like enthalpy, entropy. It is all available in the steam table. Just you copy that one and you have to enter given data. Okay, for entering this data only carries 2 marks for entering the values of enthalpy, entropy from the steam tables. Okay, corresponding to pressure of 0.1 bar, we are getting specific volume HF2, that is sensible heat, and then HFG2 is nothing but your latent heat. Hg2 is, it is enthalpy of super heated steam. You remember Fg means latent. F means F means latent. Uh, Fg, and then G indicates your gas, is nothing but superheated steam. That is the notation. HF is sensible heat, HFG is latent heat, and Hg is your total heat. Okay, that is sensible heat plus latent heat. These are the properties we are getting from the steam tables for superheated steam. Okay, next you have to apply the formula. Normal formula is what? H2. Okay, our aim is to find out H2 equals to H2 dash, because we are going to deal with the actual enthalpy. H2 dash is nothing but HF2 plus X2 into HFG2 dash. You remember for any wet steam, the formula is H equals to HF plus X into HFG. Same thing we have to apply to the point 2. That is H2 dash equals to HF2 HF2 plus X2 dash into HFG2 dash. Okay, so here all the values we are getting. Okay, here dryness fraction of the steam is given as 90% dry, so you have to take the X2 value as 0.9. Okay, 191.2 is your HF2 from the steam table, plus 0.9 is the dryness fraction. HFG2 is the latent heat. Once again, we are getting from the steam table, it has 2392.9. Just you substitute all the values. We are getting the enthalpy at 0.2 dash, that is actual point. 191.8 plus 0.9 into 23992.9, that is 2345.41 kilojoules per kg. This is what we found out. This is the enthalpy at point 2 dash. Now same formula you are going to apply for point 2. Point 2 is H2 equals to HF2 plus X2 into HFG2. That's it. You remove that dash and you have to apply the enthalpy for point 2. H2 equals to, you can see the equation number 2, H2 equals to HF2 plus X2 into HFG2. Okay, but so the ideal we don't know. Actual, they have given the dryness fraction as 0.9, but the ideal dryness fraction is not given. So you have to find out that value. So that value differs from the actual dryness fraction. Okay. So you remember actual is different and the ideal is different. Actual is we are given in the problem as 0.9. So our aim is to find out what is the dryness fraction using the ideal condition. Okay. So ideal condition is nothing but X2. Okay. So you have to apply the formula H2 equals to HF2 plus X2 into HFG2. Okay. X2 is unknown thing. And now you refer once again the TS diagram. In the TS diagram, the value of entropy at 1 and 2 are same because it is the adiabatic expansion, adiabatic or isentropic expansion, where the entropy remains constant. Whatever the entropy at 1 is exactly same as that of the entropy at the point 2. Okay, next, so once again you have to apply, that is S1 is exactly similar to our S2. Okay, now once again you have to apply the formula S2 equals to SF2 plus X2 into SFG2. How we are applying the enthalpy? Same way we have to apply for entropy also, that is total entropy equals to SF plus X into SFG. And same formula are going to apply for enthalpy also. What is the enthalpy? H equals to HF plus X into HFG. Same way we are going to apply the formula for entropy also. S equals to SF plus X into SFG. Here S2 is nothing but your S1. As I said in using the TS diagram, S1 and S2 are same. So S2 is nothing but our 7.1251. What we are getting from the steam table, that is 7. You see the value 7.125 is S1 and is exactly same as that of S2. Okay, so 7.1251 and SF2. SF2 you have to take at condenser pressure. Okay, at point 2, SF2 is 0.6493. 0.6493 is SF2. Okay, what we have written, plus X2 is unknown thing, and SFG2 once again at condenser pressure, this is the value. So we are getting the ideal dryness fraction as 0.863, but actual dryness fraction is our 0.9. So equation number 2 becomes, substitute the value. So HF2 is there, HF2 from the steam table, X2 just now we got 0.863 and HFG2 is once again from the steam table corresponding to pressure of 0.2 bar, that is condenser pressure. So we are getting H2 equals to 2256.8. Why you are calculating H2 means this is required to calculate the efficiency. Okay, so what is the efficiency? No, we are going to calculate the efficiency. For that purpose you are going to require the value of H2. Now they asked the turbine efficiency. The turbine efficiency, as I said, this is the actual enthalpy drop divided by ideal enthalpy drop. Okay, H1 we are getting from the steam table. H2 dash just now we calculated. H2 dash is 2345.41 and H2 is once again we calculated just now as 2256. So using all the values we are going to calculate the efficiency of the turbine. Okay, efficiency of the turbine is H1 minus H2 dash. H1 is 3052.1. It is from the steam table. ಹಲೋ, ಹೌದು, ಅದು ಆಮೇಲೆ ಹಚ್ತೀನಿ ಹೇಳು. Okay, 3052.1 H1 minus H2 dash, whatever we calculated, and then H1 minus H2. We are getting the efficiency as 88.8 percentage. This is the efficiency of turbine, but efficiency of the cycle is different. Efficiency of the cycle is given by net work done divided by heat supplied. Net work done is WT minus WP. In this problem, neglecting the pump work. You remember the pump work is always negligible in case of steam power plant. The quantity is very less as compared to the turbine work. Okay. So WT minus WP divided by QS. WP is 0 and WT is nothing but H1 minus H2 dash. Here you have to take the actual enthalpy. Don't take ideal enthalpy. So whenever actual enthalpy is given. So WT is H1 minus H2 dash. H1 is from the steam table 3052.1 and H2 dash we calculated 2345.41 divided by H1 minus H3. Okay, H1 minus H3. H3 you remember, okay, how to calculate H3. Okay, as I said, the whatever the enthalpy HF2 and H3 both are same. So HF2 is the sensible heat, same value we are getting at 0.3. So sensible heat means it is in wet condition. So H3 directly you take it as HF2. HF2 from the steam table is HF2 from the steam table is 2392.9. Same value you have to take. Okay, H2, H3 and HF2 both are same. Okay, so same value we have to take to calculate the heat supplied. Okay, H1 minus H3. So H1 is 3052.1 minus H2 dash is we calculated H2 dash is 2345.41. Okay, divided by H1 is same 3052.1 minus H3 is 191.8. Okay, 191.8 is, as I said, HF2 and H3 are same. Okay, so H3 no need to calculate, directly you take the value of HF2. Okay, HF2 and H3 are same. So H1 minus H2 dash divided by H1 minus HF2 or H3. Okay, so by calculating this one, we are getting the efficiency as 24.7 percentage. This is the efficiency of actual Rankine cycle. Whenever dryness fraction is given in the problem, so you have to go for the actual Rankine cycle. Okay. Okay, now I'll solve one more problem. Okay, so this is the problem. Okay, just try to understand. Major thing is, first you have to draw the TS diagram showing all the points properly. Next you have to refer the steam table and corresponding to boiler pressure and condenser pressure, you have to get all the values like enthalpy, entropy and specific volume, etc. Okay. Next, 40 megawatt steam power plant working on Rankine cycle operates between boiler pressure and condenser pressure. Okay, for all the problems they will give the boiler pressure. Boiler pressure is high, you remember, whereas condenser pressure is less. The boiler pressure is 4 megapascal and condenser pressure is 10 kilopascal. The steam leaves in the boiler and enters the steam turbine at 400 degrees Celsius. Okay, the whatever the steam leaves the boiler and enters the steam turbine at 400 degrees Celsius. This is what the temperature of the steam enters into the turbine. The isentropic efficiency of steam turbine is 85%. In the previous problem, we found out the efficiency of the turbine. Okay, in this problem, they have given the efficiency directly. The that is efficiency of turbine means what? H1 minus H2 dash divided by H1 minus H2. That is the efficiency of turbine. Efficiency of turbine is given. Isentropic efficiency means adiabatic efficiency. The process happens at reversible adiabatic process. That's why it is called isentropic. Isentropic efficiency of steam turbine is 85%. Determine the cycle efficiency. So you are going to determine the cycle efficiency, the quality of exhaust steam from the turbine. Quality means what? Dryness fraction is nothing but x2 you are going to calculate. And the third part is the steam flow rate in kg per hour. And here in this problem they have given it as consider pump work, and in some problems they'll give neglect the pump work. Okay, consider the pump work means we are going to consider the pump work. Pump work is nothing but H4 minus H3, that is a pump work, and turbine work is your H1 minus H2 dash. Okay, that is the pump work and turbine work. Okay. Okay, and from giving the problem only you can analyze. Okay, here the steam enters at 400 degrees Celsius, obviously means that you can easily analyze the steam is in superheated condition, because whenever the steam is above 100 degrees Celsius, obviously it is a superheated steam. So you have to write that reason. So the whatever the steam enters into the turbine is in the superheated state. Suppose if they give the temperature above 100 degrees Celsius, you directly state that the steam is in superheated state. Okay, so and then you have to draw the corresponding TS diagram. Same thing what we wrote in the previous diagram, same diagram you are going to write. Okay, 1 2, that is isentropic expansion. 2 to 3 is your isothermal heat rejection in the condenser. 3 to 4 is pump work, and 4 to 5 is your regeneration, and 5 to 6 is your constant temperature or isothermal heat addition, and then 6 to 1 is your superheated. You remember at point 6 we are having dry steam, x is 1, and you have to take little bit above this point, that is called as between 6 to 1 is the amount of heat supplied to increase the temperature of dry steam into superheated steam. That's why you have to take one inclined line from 6 to 1. Okay, then after that you have to locate the ideal point and actual point. So whatever the diagram we wrote, it is the ideal cycle, and actual cycle just you have to draw 2 dash point, and then you have to join this one. Okay, so first for all the problems, so you have to draw the TS diagram properly. Once you draw the TS diagram, so it is very easy to solve the problem. Okay, so this is 2 dash, this is the actual Rankine cycle. And once you draw the TS diagram, so you have to write the given data. Given data means what? Capacity of power plant is 40 megawatts. Mega means what? 40 into 10 to the power of 6 watts. So in terms of kilowatt, it is 40 into 10 to the power of 3 kilowatts. Okay, first you have to express that megawatt into the kilowatt, that is capacity of power plant, means whatever the power generated in the steam power plant is 40 megawatts, that is 40 into 10 to the power of 3 kilowatts. Okay, and then after that you have to write the boiler pressure and condenser pressure. So boiler pressure is 4 megapascal. So preferably you have to write the pascal into the bar. Megapascal means what? 10 to the power of 6 Pascal, or 4 into 10 to the power of 6 Pascal. In terms of bar, it is 40 bar. So conversion factor is most important. 4 megapascal in terms of bar, it is 40 bar. And once again, 10 kilopascal is there. So in order to make the confusion, they will give the pressure in terms of megapascal and kilopascal. First step is you have to convert that kilo or megapascal into the bar, because why you are converting into the bar means we are getting all the values in the steam tables corresponding to the bar. So you will not get kilopascal or you will not get the megapascal in the steam tables. That's why in order to get the values from the steam table, you have to convert the pascal into the bar. That is the most important thing. Otherwise, you will not get the values. Okay, these are the basic steps you have to remember. That is 4 megapascal is 40 bar and 10 kilopascal is 0.1 bar. 10 kilopascal means what? So 10 into 10 to the power of 3 Pascal. Okay, so suppose you are converting in terms of bar, so you will get 0.1 bar. Okay, and T1 superheated temperature is given it as 400 degrees Celsius, because the whatever temperature is above 100 degrees Celsius, hence the state of the steam is in superheated condition. Okay, now same formula you have to apply. How you applied in the previous formula, same formula we are going to apply. What is the formula for efficiency of turbine? H1 minus H2 dash divided by H1 minus H2. So this is your uh, efficiency of turbine. Similarly, you can find out the efficiency of the pump also. That is the ideal divided by actual you have to take. That is H1. Suppose if they ask the pump efficiency, means you have to take uh, ideal to actual. That is H4 minus S3 divided by H4 dash minus S3, like that you have to take. But here in this problem, they have given the turbine efficiency. Turbine efficiency is H1 minus H2 dash divided by H1 minus H2. How we did in the previous problem, same thing. Okay, so it is given in the problem, that is 0.85. Okay, just you call it as some equation number 1 or 2. Next, Rankine cycle efficiency is net work done WT minus WP divided by QS. This is a standard formula for all the problems. Okay, next, what is work done? Okay, work done in the turbine is, as I said, H1 minus H2 dash. Whenever the actual is given, go for actual one, don't take the ideal one. Okay, so H1 and H2 dash is nothing but 0.85. So here you have to use this equation. So H1 minus H2 dash equals to 0.85 into H1 minus H2. So H1 minus H2 is equals to 0.85 into H1 minus H2. You call it as equation number 2. First you write equation number for the efficiency of turbine. Then from this equation, just you write H1 minus H2 equals to 0.85 times H1 minus H2. You call it as equation number 2. Okay, first you write the basic formula. Then once you write the formula, you go for the steam tables. Okay, so from the steam tables corresponding to pressure of 40 bar and 400 degrees Celsius, you go for 40 bar pressure. And one more thing you remember, so you are having a heading called as superheated steam. Don't take the normal properties. I am telling again and again. So suppose you take normal properties, it is wrong. So in the steam table, they are mentioning clearly, go for superheated steam, because the steam is above 100 degrees Celsius. At the pressure of 40 bar and 400 degrees Celsius, we are finding out the properties of steam as H1 is some 3215 and SG1 means it is nothing but your entropy. You are getting these values from the steam tables. Okay, so you have to refer superheated steam properties, not normal steam properties. So whatever beginning you are having, those are all related to your wet steam. So after that, we are having a table called as superheated steam. Next, at condenser pressure of 0.1 bar, so we have to find out the value, specific volume. It's once again from the steam table. One is with respect to 4 bar boiler pressure, and one is with respect to your condense bar. Okay. Tell me any doubts, Tarun? Okay.
No, sir.
So just I'll continue. Okay. So you have to take the steam properties at 40 bar and 0.1 bar. So these are all the values you are getting from the steam tables only. Okay. So I have posted the steam tables. Meantime, suppose if you are having steam tables, you can refer it. Okay. So Vf and V3 both are same, and HF2 is what? Sensible heat. Okay, you remember at condenser we are having the wet steam, at boiler we are having superheated steam. So HF and HFG comes into picture only in case of 0.2, not in case of 0.1. HF2 and HFG2, that is one is sensible heat and one is latent heat, and SF2, and these are the all properties what you are getting from the steam tables. Okay, hence steam tables plays very important role in vapor power cycle. Without steam tables, you are unable unable to solve the problems. Okay, at least you write the values how much you are getting and you apply the simple formula. Okay, so formula are not complicated. Okay, here very simple formula. Okay, next you have what is the equation number uh, okay. Now Wt is H1 minus H2 dash. It is nothing but 0.85 times H1 minus H2. So H1 what we are getting from the steam tables. So Wt is 0.85 into H1 what we are getting from the steam table minus H2 you put as it is, but we don't know the value of H2. Okay. First substitute all the values. So Wt is you are getting H1 minus H2 dash equals to 0.85 times H1 minus H2. H1 you are getting from the steam tables 3215.7. So how to find out H2 is you have to apply the formula. This is a standard formula. The total enthalpy is sensible heat plus dryness fraction into the latent heat. So HF2 is 191.8 from the steam table corresponding to pressure of zero point 0.1 bar. That is condenser pressure. X2 is dryness fraction. We have to find out the dryness fraction into HFG2 means 2392.9. It is once again corresponding to pressure of zero point 0.2 bar. Okay, here the process is same in all the problems. That's why I try to understand one problem properly. Then how to find out X2? Once again, you have to refer this TS diagram. As I said, S1 and S2 are same because it is the isentropic expansion. The entropy at 0.1 is same as that of the entropy at 0.2. So whatever S1 you are getting from the steam table, same thing you have to write for 0.2 also. So S1 and S2 are same. And what about S2 formula? S2 formula is, as I said, SF2 plus X2 into SFG2. The same formula holds good for your the enthalpy also. Instead of S, just you change it as H. Okay, and the formula is same. H2 equals to HF2 plus X2 into HFG2, or entropy is S2 equals to SF2 plus X2 into SFG2. You remember, so S2 is they have shown SG1. It's wrong. It is S2 actually. S2 and S1 are same. S1 is 6.7733 from the steam table, and SF2 from the steam table corresponding to pressure of 0.1 bar condenser pressure. X2 is unknown thing. SFG2 is once again from the steam table corresponding to pressure of 0.1 bar, that is condenser pressure. So after solving this one, we are getting the X as 0.816. You remember you should get the value less than 1 only, then only your answer is correct. Suppose if you're getting more than 1, it is wrong. Okay, so because the whatever the condition of the steam in the below saturated curve is your wet steam. Okay, so after calculating X2, you have to substitute back in H2. H2 equals to substitute the value. H2 equals to 191.8 plus X2 is just now we calculated 0.816 into 2392.9. So after substituting all this value, we are getting 2144.4 kilojoules per kg. Okay, so calculation of H2 is most important. Okay, so you have to calculate dryness fraction, then you have to substitute back. So that is 2144.4 kilojoules per kg. Now, so next you have to substitute back in equation number 3. Okay, so what is Wt? 0.85 into 3215.7 minus H2. H2 just now we calculated it as 2144. So after substituting the values, we are getting the work done by the turbine is plus value will get 910.6 kilojoules per kg. Okay, next in this case they have asked pump work. Okay, sometimes they will ask neglect the pump work, but in this problem, so they have given pump work. Pump work means what? Just once again you refer the TS diagram. That's why TS diagram is most important. Turbine work is H1 minus H2. Pump work is H4 minus H3. That is the pump work. Turbine work is H1 minus H2. And 2 to 3 is your isothermal, the heat rejection, that is condensation work. So 4 to 3 is your the pump work. So you have to write the formula. So H4 minus H3 equals to, and once again I said, so you have to use one more formula. Both are same. You can write V3, that is specific volume into boiler pressure minus condenser pressure. Okay, this is either you can use this formula or this formula to find out the pump work. Okay, so that's why you have to remember both the formula, H4 minus H3. Okay, why you are using this formula means we are going to calculate all the things. It is a very difficult process, hence you have to remember this formula, V3 into PB minus PC. V3 what you are getting from the steam table, that is 0.0010. This is corresponding to condenser pressure, you remember, and V3 is nothing but your specific volume. And PB and PC, what I said, first you have to convert kilo into bar. Always you have to express in terms of bar. Don't use either megapascal or kilopascal. So boiler pressure is 40 bar and condenser pressure is 0.1 bar. So into one more thing here, what we are getting, you have to express in terms of kilo units. That's why multiply by 100. Okay, so you're getting the pump work as 4. You remember the pump work will get very less value as compared to your turbine work. Pump work is approximately 4 kilojoules and turbine work is 910, almost 250 times greater than. Okay, that's why in most of the problem they'll uh, tell to neglect the pump work, but in this problem they asked to calculate the pump work, hence you have to calculate the pump work. You see the magnitude, one is 4 and one is 910. Pump work is very less as compared to your turbine work. Okay, so this is how to calculate the pump work. Next step is amount of heat supplied. Why amount of heat supplied is required means we have to calculate the efficiency. The standard formula for efficiency is what? Net work done divided by heat supplied. Net work done is your turbine work minus pump work divided by heat supplied. So what is the heat supplied? Okay, heat supplied. Now once again you refer the TS diagram. Heat supply takes place between H1 and H4. H1 minus H4. As I said, don't consider this 5 and 6 in the problem directly. You have to take 0.1 and 0.4. So because the amount of the heat supplied, whatever it is coming out from the pump, it enters into the boiler. That's why you have to take H1 minus H4. Okay, so H1 minus H4 is the amount of the heat supplied to the water to convert into the steam. That is amount of heat supplied. QS is H1 minus H4 and H1 minus H4. Okay, then what about pump work? Pump work is what? H1 minus pump work just now we calculated H1 H4 minus H3. Okay, so here once again you have to apply the pump work, but we H1 we know, but we don't know H4. Then how we are going to calculate H4? By means of this, you have to refer the above equation. WP is H4 minus H3. Okay, so H4 is nothing but H3 plus WP. WP is pump work, and H3, as I said, for all the problems H3, that is enthalpy at 0.3 is always equals to HF2. In all the problems you take directly H3 and HF2 are same. HF2 is what? It is the sensible heat at condenser pressure of 0.1 bar. So H3 and HF2 are same. So WP is the pump work is H4 minus H3. So we know this H4 is nothing but WP plus H3. So H3 is nothing but HF2, that is 191.8 plus WP is your pump work 4.03. So after simplifying, we are getting 195.83 is your H4. Okay, why you need H4 means to calculate the amount of heat supplied. Now substitute the value of H4 in this equation number 5. QS is H1 you are getting from the steam table, and H4 just now we calculated it as 195.83. So after substituting, you are getting the QS as 3019.87. Okay, now you have to apply the standard formula, that is WT minus WP. WT is 910.6. WP is pump work 4.03 divided by heat supplied is 3019.87. So 0.3, around 30 percentage. Okay, this much, this is the range what we are getting in between 20, 30, 35. That is the range of Rankine cycle efficiency. Okay, this is the how to calculate the Rankine cycle efficiency. Okay, now quality of the steam. Okay, how to calculate the quality of steam. Quality of the steam means you have to calculate your x2 dash, because it is the actual Rankine cycle. So H2 dash equals to HF2 plus x2 dash into HF Z2 dash. Okay, but H2 dash we don't know. So H2 dash, how we are going to calculate? Once again, you have to apply the efficiency of turbine formula. H1 minus H2 dash divided by H1 minus H2. So efficiency of turbine is given in the problem 0.85. H1 from the steam tables, and H2 dash we don't know. H1 is 3200 minus H2. Just now we calculated using the formula. Okay, H2 I will tell. H2 is uh, okay, H2. Okay, here H2 is there. Okay, H2 we calculated it as 2144. Okay, this is H2. So our aim is to find out x2 dash. So in order to find out x2 dash, we need h2 dash. How we are going to calculate h2 dash means eta t equals to h1 minus h2 dash divided by h1 minus h2. So you have to apply eta t is given in the problem. All the values we know except h2 dash. Once you know h2 dash, so you have to substitute back in equation number 6. Okay, equation number 6 is h2 dash equals to hf2 191.8 from the steam table. X2 dash is unknown thing. Okay, and 2392.9 is hfg2 dash. Okay, so this is from the steam table, you remember. So after substituting all the values, we are getting the dryness fraction x2 dash. It is a 0.883. Okay, so around 88.3 percentage of dryness fraction what we are getting at 0.2. Okay, don't take ideal one. Okay, you have to take the actual one. Okay, and the last part, how to find out the steam flow rate, how much quantity of the steam is flowing in the steam power plant. Okay, see the last part. Okay, last part is power. You know the power formula. Power formula is net work done divided by uh, so this is the rate of doing work. Power is net work done per second. Okay, so power is given in the problem. How much? 40 into 10 to the power of 3 megawatts is given. So we have converted into 40 kilowatts. M is nothing but your mass flow rate. You remember this formula, mass flow rate into the network. Sorry, it's a network. The network done is nothing but WT minus WP. Okay, just unknown thing is your M dash. You remember the power formula is net work done divided by per second, means what? WT minus WT into mass flow rate. That gives your power. Power is given by mass flow rate into the network done is nothing but the power. Power is given in the problem 40 into 10 to the power of 3. M is mass flow rate, WT minus WP. So 40 into 10 to the power of 3. M is unknown thing, mass flow rate. WT and WT we calculated. Okay, so substitute all the values. You'll get the answer in for kilojoules per kilogram per second. Okay, and you have to convert in kilogram per hour by multiplying this value with 3600. So you'll get 1,58,832 kilogram per hour quantity of the steam is flowing in the steam power plant. So the whatever problem I explained, so this kind of the problem only they'll ask in the exam. So this covers the entire thing. This problem number, you remember, note down problem number 7 and 8 I solved today. This problem number 8 is most important. Okay, so it covers entire thing. Okay, I have posted all the problems in the Google Classroom. Just you refer today once again. Okay, try to analyze the problem. Such kind of the problem they'll ask in the exam. Okay, meantime you refer the steam table, get the properties properly to find out the efficiency, to find out the mass flow rate. Okay, such kind of problems they'll ask in the exam. Okay. Darshan, Darshan,
Yes, sir. Yes, sir.
understanding Darshan?
Yeah, yeah.
Any doubts? You know how to see the steam tables? Okay.
Yeah, sir.
Good. Okay. Just today, once again, go through the problems, sir. I have posted all the problems in your Google Classroom. Okay. So just refer it. Try to analyze one problem. Okay. Still your handouts, ask me. Okay. Okay. Abhishek Haniyur. Abhishek Haniyur. Abhishek Haniyur. Abhishek. Okay. Try to complete your assignment too, and all of you have to upload your assignment too in the Google Classroom. Okay. So that is the procedure. Okay. Yeah. Go to your class code. Okay. So you have to upload all the assignments in Google Classroom only. Okay. Okay. Thanks, students, for joining the class. Okay.